All right, so in our last video, we reviewed a lot of the big concepts from chapter 3. We learned how to do LSRL, least squares regression line stuff, including slope, y-intercept, interpreting residuals, r squared s, all those different pieces that go into analyzing a scatter plots. What we're going to do in this section is take all of those scatter plot line of best fit features and turn them into 4-step style questions. So we're going to want to make either a confidence interval or run a significance test on a line of best fit problem. And we'll show why that's helpful and important as we progress through our activity here. So our first data set for the day here, I believe if I remember correctly, we are looking at Old Faithful. The guys are in Yellowstone, and we're looking at how long when it, like the geyser erupts, how long it erupts for. And then for the y-axis, we're looking at how long it is between the geyser going off, so the interval between eruptions. And what we have here is the complete population of the eruptions and times in between for a certain time frame. So this is all of them in this top picture. This is going to be our population up top, meaning that this line of best fit that they drew here, that line is our true LSRL. That's the real deal right there. Now, what we're doing in these smaller pictures below is we're illustrating what would happen is that instead of having the entire population, we had a random sample of, I don't know how many dots that is, 15 to 20 dots. So out of all these dots in this top picture here, I scoop up a random sample. I get these dots in this bottom left picture, and I would draw this line of best fit right here. So this line of best fit is going to end up being kind of different than the first one I put above based on the points that I end up getting. So if you look at the equation here, totally not an exact match. When I compare this guy to this guy right here, there's definitely some fluctuation going on. If I look and take a different sample of 15, 20 dots, I get yet again a different line of best fit. And if I do it a third time here, I get yet another line. So depending on which dots we scoop up out of our population, we're going to have different lines of best fits. So that is kind of the driving force behind what we're doing in this section. You're not going to have the whole population. You're going to have a sample of dots, and you're going to have to make a line of best fit and try to guess the true line based on the data you have at hand. So that's where we're moving towards in this section. In order to do these problems and run inference on least squares regression, there's a whole host of 5 new conditions right here. There's a lot of stuff you need to check. The conditions, if you're looking for a way to remember them, it does spell out the word liner, L-I-N-E-R. But I'm actually, in AP Stats, not going to go into these conditions and get into the nitty-gritty here. These conditions are important. I'm not trying to claim that they're not, but for our purposes in AP Statistics, this is a lot to learn here at the very tail end of our class. So what I will usually have you guys do is say something like assuming conditions are met. These conditions are more challenging than what we're used to. And it's a whole new list you'd have to learn and practice on. I'm just going to have you guys say on the AP test, hey, let's assume our conditions are met. Now, if they're not met and you were supposed to verify them, you would lose a little credit on the AP test. I don't see that happening, though. Certainly not very frequently. Sorry if you guys are like the year where it happens to be on there. But I feel pretty strongly they're not going to ask about that. And if they do, it's a small thing. So when you do a chapter 12 LSRL type problem, you're going to say something to the effect of assuming conditions are met. And don't worry about learning this list right here. So a couple more pieces that we need to build before we can actually go and do our 4 steps. When you do a line of best fit type problem, you need to set it up in the form. We would talk about how it went y hat equals a plus b times x. So this is like how we typically write a line of best fits. You know by now that when we do parameters like the true values, we like to use fancy Greek letters for them. So like we use mu or we use sigma, stuff like that. So the true line of best fit equation, not just from like some random sample, this would be what you would use if you were doing a sample LSRL. If you have the true population LSRL, what you're going to end up doing instead is putting the following. A, our true parameter for A is going to be the Greek version of A, which is alpha. And our B right here for the slope, we use the Greek letter beta. So if you want the true line of best fit, that would be like my first picture, way up here at the top. This guy up top would be a situation where you would have alpha plus beta x. All of these came from samples. These would be written in the form y equals a plus b to the x. So when you do problems involving LSRLs and you're doing like inference on them, the three parameters that we may choose to estimate are going to be alpha, which is your y-intercept, and to use, so this is the parameters over here. The statistic version of that is going to be A. So in a sample, we would call it A. We're looking for alpha. Not to be confused with alpha in significance testing, like the 0.05 significance level. We just use the same exact Greek letter for a different meaning here. The second one we have in our little LSRL equation is beta. Beta is going to represent the slope of our regression line, and we use the symbol B for that. The last thing we may want to estimate in a LSRL problem is actually going to be sigma. Sigma is going to be the standard deviation of the residuals. You guys will know this by a much more common name of S. This is that S that I would always have you estimate in LSRL problems before. So like if you look down below this S right here, this is the sample version of sigma, which is the true standard deviation of the residuals. So these are the three variables you may want to estimate. By far, the most important in this chapter is going to be the slope for reasons we will end up discussing. So we have more pieces we have to put in place here before we're ready to do inference. The standard error of the slope. That is something we've talked about. We've talked about standard deviation, standard error at different points in the class here. The standard error or standard deviation, when we talk about it, it's basically referring to how far off we think our results might be. It's our estimates of the spread of the sampling distribution of our sample slope is usually the one we're estimating here. So it's looking at, if you take lots of different samples, how far typically will our sample slope be from the true slope, which is that beta that we talked about earlier on. This is on your formula sheets, but you won't want to use it. It's a lot of work. So you won't want to use it. I think I pulled it up here. Got like 12 tabs open. But if you look on your formula sheet second page, we're all the way finally at the end of our formula sheet. When you're doing stuff on slope, the standard deviation of the residuals is the standard deviation of your slope is going to be right here, our little standard deviation guy. But usually you're going to do the standard error instead, which is the version with S plugged in, because we're not going to know actual sigma. You're not going to want to use this formula at all. What's probably going to happen is they will give it to you on like a little table, like you'll see down below. So we'll put all this together and make it make sense in just a bit. The way that I want you guys to interpret your slope, you're going to end up talking about if we repeat our data collection many times, the slope of our sample regression line typically varies from the true slope by about whatever it ends up being. That'll make more sense when we actually do an example here. So we've got our seating chart problem to make sure this is making sense. And this is very much what you will be expected to do. They're not going to make you use the formula I showed you a minute ago. So we look at these numbers right here. This is for our LSRL itself. So we would know it's 85.7 plus negative 1.11x. These numbers right here, these SE, standard error numbers, we never worried about those back in chapter 3. But in chapter 12, we actually do care about the one on the same row as our slope, which is going to be this 0.9472. So the symbol for standard error, you can do S with a B, or sometimes you'll see SE with a B. I would be okay with either of those. The value of that quantity is 0.9472. So I'll write this here, but I'm going to pause my video and just pop it up there. Basically what we're talking about is if you do lots of samples for this like row seat that you're in versus your test score, if we take lots and lots and lots of samples, our sample slope, our B, will typically be off from the true slope by about 0.94. All right, so I wrote down a little script, very light on context. Honestly, I might take off for my own answer here. If this was a quiz, I would need to tie it back in. When I'm talking about the true slope, I would need to talk about the true slope for test score using the row that you're sitting in, predicted test score. Just put a little more context in it. I also noticed after I paused here that this was an experiment. We were randomly assigning people to the row that they sit in rather than random samples, but the same concept holds. If we did this lots of times, our slope would be off on average by about 0.94. So that piece is actually going to be relatively important in learning how to make a confidence interval for our slope. So we're going to focus in this chapter on making confidence intervals and running significance tests on beta, on that slope. The reason the slope is so important when we do a problem like this, if we know for a fact that our slope has to be positive, that tells us something about our variables. That tells us that, oh, as the one variable goes up, so does the other. So if you do an interval for the slope, and your interval is all positive values, it goes like, I don't know, here, that's a big deal, because that tells you there's a positive association between the variables. Similarly, if you do a problem and there's a negative association going on, and your slope is all negative values, I don't know, I'm just making random things up here, that's also a big deal, because now you know the variables have a negative relationship. What we're going to end up looking for is whether 0 is in this interval. So say my interval goes like this. Well, this, I don't know. My variables could have a positive association. They could have a negative association. They could be none at all. This is like, I can't tell what's going on right here. So we run our tests on the slope, because a positive slope versus a negative slope versus could be 0 slope lets us know if there's a relationship probably going on or not. So that's why we care so much about beta. So when you make confidence intervals for a slope, the actual formula or the setup you're going to use, we're making confidence intervals for beta here. Remember how that goes. When we do this, we start with our statistic. So it's going to be statistic plus or minus your critical value times the standard deviation or the standard error, depending on which one you have. That's why I made us refresh standard error just a minute ago. So our statistic in a slope problem is going to be our sample slope, which we use little b for that. The critical value for a problem on a slope or a least squares regression, it's quantitative by nature. So we are going to use a t distribution, just like we would do with mu problems. So it is a t distribution. And then you're going to multiply by the standard error. I'm going to go SB, or you can go SE of B, which is what you usually get from our table. The difference on these problems here, your degrees of freedom for your test statistic, for your critical value, it's going to be not n minus 1 like we did in a mu problem, which has just one parameter, we're going to do n minus 2 because we are connecting two variables here when we do least squares regression instead of just one. That's a little bit of a hand-wavy explanation for why, but you do use n minus 2 for your degrees of freedom. So now we're ready to kind of put stuff together here, and we're going to learn how you would actually construct an interval for our seating chart problem. So my little seating chart box right there, that's based on one random assignment, one like sample that I collected data on. And my sample slope when I did that was that negative 1.1171 number. So that is where I start my interval. That's my B. So I got negative 1.1171. Plus or minus, I need to find my T star, which means doing an inverse T, if you guys can remember that. On a 90% confidence interval, my middle area is 0.9, meaning that each tail is 0.05. So I can just do inverse T. My left area is 0.05. And my degrees of freedom on this problem, I'd have to go back up and figure out what my sample size was. I have written down, actually that's not even on, it's a long ways back. The sample size for that problem was 30. So I'm gonna have 28 degrees of freedom when I do this. If you do that in the calculator, remember it's gonna give you a negative critical value because it's giving you the left side of the picture. You just drop that negative off. So it will tell me that my T star, if you type that in, it's about negative 1.70. We're gonna turn that to a positive for our critical value right here. And we're gonna multiply that by the standard error of our slope, which is in the little table, the SE column. For slope, it's 0.9472. So 0.9472 is gonna end up being our standard error. Then you're just gonna do your pieces right here. This is gonna end up getting you the interval from negative 2.727 to positive 0.493. So if I was gonna interpret this interval, what I would say is that we are 90% confident the true slope for that least squares regression line is somewhere between a negative 2.7 and a positive 0.493. Think about that and process that for just a second in terms of what that tells us. What that's saying here, our slope for the least squares regression line could be a positive number. It could also be a negative number. It could also be 0. In other words, we have no idea what's going on with rho and test score. Could be helping it, could be hurting it, could be doing nothing. If I was eventually doing a significance test, which we'll get into in the next video, we would have no idea what was going on. We'd fail to reject the idea that there was any sort of connection here. So when you make your confidence interval, what we really care about is that number 0, kind of like we did in earlier chapters. So in our next video, we're gonna pull together a full 4-step on the confidence interval type problem. And then we're gonna finish up by also doing a significance test to practice that as well.